Welcome to section 7.5. Today is an exciting day because today we're going to complete the Laplace transform circuit that I showed you back in the beginning of the chapter. So we're actually going to solve problems by going all the way around this circuit. We won't be able to solve problems like the one in this example yet, but that will come soon. A comment on notation as you solve initial value problems with Laplace transforms. The first line of every solution should show you taking L of both sides. Again, that's a courtesy to someone reading your work that that's what you're going to do on the next line. Then you're going to do your main work. So there might be many lines of the main work, but the last two lines of your solution should look like the penultimate line should be y equals L inverse of whatever you're going to take the inverse transform of. And your final answer is y equal your final answer. And don't get creative, please. Keep that to writing classes. Put y equals final answer, not final answer equals y. The y goes first. Okay, so let's get started. This is number 6 from your textbook. I'm going to take L of both sides. So L of y double prime minus 4y prime plus 5y equals L of 4e to the 3t. Okay, now we're actually going to do that. So as I take L of y double prime and L of y prime, I'm using formulas 19 and 20 in your table, and I've replaced little y with little f and and big F is big Y. So we're just changing F's to Y's. So I'm going to go through this fairly quickly, but it might take you a little longer at first when you're getting started. S squared, big Y, minus S y of 0. Y of 0 is 2, so that's minus 2s, minus y prime of 0, so minus 7, minus 4, use parentheses so you don't forget to distribute. L of y prime is S big Y minus y of 0, which would be minus 2. And then L of 5 little y is 5 big Y. L of 4e to the 3t, using formula 3 from your table, it's going to be 4, which is a constant that carries along, over s minus 3. Okay. Next step. Leave every term that has a big Y in it on the left and factor out the big Y. So on the left, I get big Y, s squared minus 4s plus 5 equals, let's see, I'm going to bring the 2s over because that has no y in it, and it becomes positive. And then I've got minus 7, but I have a plus 8, so that's plus 1, so that comes over as a negative 1. And then plus 4 over s minus 3. Now, I'm going to write this as a single fraction. This is, the common denominator would be s minus 3. So I need to multiply this 2s minus 1 by s minus 3. And then add 4. All right. And we'll clean that up on the next step. So now I'm going to divide both sides by s squared minus 4s plus 5. So big Y is, make a big denominator. On the right over here, I'm going to have s minus 3. And then s squared minus 4s plus 5. Then on top, let's clean this up. This is going to be 2s squared minus 7s, and then plus 3 plus 4 is plus 7. Now, I'm going to use partial fraction hint up here at the top. You can see I have that expression on the left and the partial fraction decomp on the right. And so when I take L inverse, so my next line is going to be little y, and if I can't distinguish between your little y and your big Y, then you can write little y of t just to make it super clear. Little y is L inverse of this fraction right here, but I'm going to write this down in the decomposed form. So that's 2 over s minus 3, and then plus 1 over, I'm not going to just write s squared minus 4s plus 5, because I have to take the inverse transform of that. It doesn't factor, so I can't use partial fractions on that. However, I can complete the square on that, s minus 2 quantity squared plus 1. That's the same as s squared minus 4s plus 5. So now I'm ready to take L inverse, and on this guy, I can use number 8 with A equal 2 and B equal 1. All right, and so my final answer is little y, or little y of t, whichever you prefer, is 2e to the 3t, that's formula 3, and then by formula 8, I get e to the 2t sine t. That's our answer. So let's reflect for a moment. How could we have solved this problem if we weren't using Laplace transforms? Well, we could do two things. We could use variation of parameters, or we could use undetermined coefficients. If you use undetermined coefficients, UC, remember, you can use UC when you have constant coefficients and the driving function is one of the special types, exponential, sine, cosine polynomials. We have that type. So if you use UC, you'll find that your characteristic equation is r squared minus 4r plus 5 equals 0. And that has complex roots, 2 plus or minus I. And so when you look at this solution here, this e to the 2t sine t is coming from the complex root situation, and then this part is coming from your trial yp when you use undetermined coefficients. I just wanted to mention that. Okay, I'm going to do two more with you and then talk a little bit about piecewise defined functions. This next one, there's another hint. If we write L of t squared plus 2 as a single fraction, we will not need partial fractions. So let's get started. I've got an abbreviated table on the left there. L of y double prime plus y is L of t squared plus 2. So using formulas 19 and 20, s squared big Y minus sy of 0, that would be minus 4s, plus y prime of 0, sorry, minus y prime of 0, but y prime of 0 is negative 1, so this is going to give me a plus 1, plus L of little y is big Y equals L of t squared is 2 over s cubed, and L of 2 is 2 over s. So I'll write that as a single fraction. I need to multiply this second guy by s squared over s squared. Okay, now factor out the big Y, s squared plus 1 times big Y. Move non-big Y terms to the other side. 4s minus 1 plus this fraction here, which I'm going to write as 2 times 1 plus s squared over s cubed. Now I'm going to divide both sides by s squared plus 1. So I'm going to divide each piece by s squared plus 1. So 4s over s squared plus 1, because I know I can use my table on that, and I know I can use my table on this next fraction. And for the last fraction, I get 2 1 plus s squared over s cubed times s squared plus 1. These are the same. So just 2 over s cubed, and I know I can use my table on that. So little y is L inverse of 4s over s squared plus 1 minus 1 over s squared plus 1 plus 2 over s cubed. Now this first one is formula 7 with b equal 1, and this next one is number 6 with b equal 1, and the last one is number 2 with n equal 2. So little y is, pull the 4 out, 4 cos t, and then this one's good to go, minus sine t, and then this last one would be plus, let's see, it's already in the right form, t squared. That's my answer. Okay, one more. This is number 8 from your textbook. I've given us a partial fraction hint. So at some point, we're going to end up with an expression like the one on the left. Here we go. L of y double prime plus 4y, that's it, is L of 4t squared minus 4t plus 10. That's our courtesy step. It's like using your blinker. You're telling people what you're going to do. Next, s squared big Y minus sy of 0, so, but y of 0 is 0, so just s squared big Y minus 3 plus 4 big Y equals, I'm going to get 2 factorial over s cubed, 2 factorial is 2, 2 times 4 is 8 over s cubed minus 4 over s squared plus 10 over s. I'm going to write all of that with denominator s cubed. 8 minus 4s plus 10s squared. Okay. S squared plus 4, factor out the big Y. Those guys stay on the left. And then 3 comes over to the right. Positive 3. 3 plus 8 minus 4s plus 10s squared over s cubed, which I'm going to write with denominator s cubed. So that's going to be 3s cubed plus 8 minus 4s plus 10s squared over s cubed. Finally, we're going to divide by s squared plus 4. Big Y is, so that numerator, 3s cubed plus 8 minus 4s plus 10s squared over s cubed, I didn't need parentheses there, s squared plus 4. I did need them there. Okay, so that is what I have on my hint. So I can go ahead and write down the partial fractions on my next step. Little y is L inverse of, I'm going to write down the decomposed form of this, 2 over s cubed. Then I'm not going to just write down 4 minus 2s over s squared plus 4, because I'm looking at this and thinking, well, if I want the inverse transform of that, I want to separate that out into 2 fractions. So that's plus 4 over s squared plus 4, and then minus 2s over s squared plus 4. I can take the inverse transform of both of those, no problem. And then minus 1 over s squared plus 2 over s. Okay, and just to let you know, this is in your table. This is going to come from formula 2. This is going to be number 6 with b equal 2. The next one's going to be number 7. That's a cosine, again with b equal 2. The next one's number 2, and this guy's number 1. So little y equals, ready to write down our answer, t squared. And then for formula 6, I would need a 2 on top. I have a 4 on top, so I'll pull a 2 off. So plus 2 sine 2t minus, this guy only want an s on the top, so pull that 2 out to the side. That's a constant, 2 cos 2t. Then minus t and plus 2. There's our answer. You could have also used undetermined coefficients on this one. I think our method was a lot quicker. All right, so you got some practice problems at the end, but I want to do a preview of the next section, just get us started here a little bit, preview of the unit step function. So the unit step function is also called the Heaviside function, and it's an on-off switch. It's defined as u of t minus a. A will vary from problem to problem. It could be 1, 2, 3, 4, but the function 0 until you get to a, and then it's 1 after a. So on and off and on. Some textbooks will have, a greater than or equal to there or there, one or the other. It doesn't really matter because it's not going to affect the Laplace transform, the value of a function at a single point. So we're going to have open on both sides. Now, what are we going to do with that? We're going to use unit step to rewrite piecewise defined functions. And so then we'll be able to use the table to find the Laplace transform of a piecewise defined function, which is pretty exciting. So there's 2 formulas here. You'll need this one to do some homework problems. You do not need to memorize it. This one you need to memorize. Mem or eyes. I forgot the R there. You need to memorize this formula because you're going to use it quite a bit. So let me just walk you through this formula and why it's true. Suppose t is less than a, then the function's supposed to be f1. So going over here, if t is less than a, the unit step is 0. So this whole piece is 0, and sure enough, f is f1, and that's what you wanted. Now, suppose t is greater than a. If t is greater than a, you want f2. Well, if t is greater than a, then the unit step is 1. So f is f1 plus f2 minus f1 times 1. So the f1's cancel, and you get f2, which is what you wanted. So that's how it works. And for 3 piecewise defined functions, it works similarly. You can go through that. So let's do a few examples here. Write f as a piecewise defined function, then rewrite it using the unit step function. So f of t equals, this one's fairly easy, 0 if t is between 0 and 1. All our functions will start at 0 and go on. So, because the Laplace transform is only defined for t greater than 0. So that's the first part. And then the function is t squared if t is bigger than 1. So our a in this formula at the top here, our a is 1. A is 1. And so f of t, I'll just plug it in and then simplify it. f1 is 0 plus f2 minus f1, t squared minus 0, u of t minus a, but a is 1. So that's it. So f of t is t squared times u of t minus 1. If t is less than 1, u is 0, and so the function's 0. And then as soon as t gets to 1, this acts like an on switch. U of t minus 1 is 1, and so f of t is t squared. So maybe you should pause the video and try this one on your own, and then unpause it, and I'll do it with you. Okay, hopefully you did that. F of t is, I'm just going to do this by inspection. For the first part, for t between 0 and 1, we've got a line, and it's got slope 3, and it goes through the origin, so 3t. For the second part, t greater than 1, we've got a line, it's got slope -1, and if I were to continue it on, it would cross the y-axis at 3. So this has slope intercept -t plus 3. Okay, and then for unit step, again, I'll go slow. First, I'll just put everything in, and then I'll simplify it. We want F1, which is 3t, plus F2 minus F1, -t plus 3, minus 3t, times u of t minus 1, because a is 1 again in this case. A is the breaking point where the function changes. So f of t is 3t plus, let's see, we're going to get 3 minus 4t times u of t minus 1. All right, let's just do one more, and this is one with a with 3 functions, an f1, f2, f3. So I'm going to be using the second formula with the a's and the b's. And let's see, f of t equals, all right, we're going to be 0 if t is between 0 and 2, and then it jumps to 1 for t between 2 and 3, and then it goes back down to 0 for t greater than 3. By the way, your textbook has another way of handling this with something called a window function, and you can ignore that. If it pops up in the help me solve this, just ignore it. I'm not going to use the window function. I'm just going to use the unit steps. I think it's easier. All right, so my A is 2, and my B is the second breaking point, which is 3. So f of t, I'm going to be using the formula at the top there, is f1, which is 0, plus f2 minus f1, which is 1 minus 0, u of t minus 2, plus f3 minus f2, 0 minus 1, u of t minus 3. Okay, so we'll simplify that to get a pretty simple function. F of t is u of t minus 2 minus u of t minus 3. All right, and in the next section, we're going to talk about taking the Laplace transform of that and working with inverse transforms.